in section 5.1, if y'all would find all the factors of 120, and the related follow-up question is find all the prime factors of 120. So think about what would be the difference in those two answers. Now, as we work through all the factors of 120, we know that always 1 divides a number, so 1 and itself and these kind of bookend each other. And then we just start going through the integers, typing it into the calculator, see that 2 divides 120 because it divides perfectly, so 2 and 60. And as we find the prime factors, it's going to kind of move inward to now we check 3. 3 also divides it, 3 and 40. See if 4 divides it, 4 and 30. Let's see if 5 divides it, 5 and 24. Let's see if 6, so 6 and 20. Does 7 divide it? If you'll notice, 7 doesn't because we have that it divides as a decimal. So next we check 8. 8 divides by 15. $120 divided by 9 doesn't divide perfectly. 120 divided by 10, 10 and 12. And now let's check 11. $11 doesn't divide perfectly. And then what do we notice about 120 divided by 12? Do you see that starts repeating things that we've already written down? So if you work this way, it's going to come to the middle until it starts repeating factors. That's when you know you're done. So these would be all of the factors of 120. Now, in our next related question, it says the prime factors. So for the prime factors, it's what are the factors, the things that divide into 120, but are also prime numbers. And you could look at this list and just identify which numbers in here are prime, and then you could find it. Or if you prefer, you could also do the factor tree method. So let's find that. So here we'll do our factor tree. We know we could find whatever is divisible by 120. As long as we go down the pattern correctly, we'll get the right answer. But if we can find something that's divisible by 120 that's a larger number, it will be less steps. So maybe we think of 10 and 12. Any number that ends in 0 is divisible by 10. And then you just keep factoring these until you get only prime numbers at the bottom. So 12 and 2 could be 6 and 2. Now 2 is prime, so that doesn't have to be split up further, but 6 could be split into 2 and 3, both of which are prime, so that's the end there. Now we need to split up 10, 2 and 5. All of these are prime. So the prime factors of 120 are 2, 3, and 5. And we would phrase this differently than the prime factorization of 120. So if you're looking for the prime factorization, if y'all would all write that out on your papers. 2 occurs 1, 2, 3 times, so we get 2 cubed. 3 occurs only once, so it's just times 3. 5 occurs only once, that's just times 5. And remember, you can always check your work. 2 times 2 times 2 times 3 times 5 is indeed 120. Any questions here? So we also know that we could be asked to, using the divisibility chart that would be provided. So this chart would be provided. But based on this chart, can we assess the correct reasoning for why one number would be divisible by a certain number? So if y'all would look at the divisibility chart and then think about why we could say 128 is divisible by 4 based on the reasoning given here, and select the correct answer. So it says if you're looking to see if a number is divisible by 4, you see if the last 2 digits listed are divisible by 4. So for us, we'd say, is 28 divisible by 4? Yep, by 7. So that would be the reasoning. And that's what we'd select. Okay, let's find the prime factorization of 160. I'll give everybody a moment to attempt on this on their own. We know we begin with the factor tree. Our factor trees might start differently, but they will end in the same place if we do it correctly. Did y'all get 2 should occur 1, 2, 3, 4, 5 times, so we get a 2 to the 5th times 5. It does check out. Good. So remember, you keep dividing until you have your prime factors. So on your formula sheet for this section, you might want to write out the prime factors less than 100 that is given in our notes, but I also will include that within the exam. But that way you don't have to scroll if you've got it on your paper, because it helps us to recognize what are the prime numbers. Now, I'll give everybody a moment to attempt to find the GCF of 124 and 64. As a reminder, if it helps, remember that you need to find the prime factorization of both numbers. And then for the greatest common factor, you choose all of the common primes, but to the least exponent possible. So did y'all get these for the prime factorizations of 64 and 124? Okay, good. So then when we were choosing the greatest common factor, we looked for what prime numbers were common in both factorizations. And y'all agree only 2 was common. But now we have to decide what exponent do we include. So for greatest common factor, you choose the least exponent possible, which for these pairings would be squared. So the greatest common factor is 2 squared, which we're comfortable is equivalent to 4 because 2 squared is 2 times itself twice. So 2 times 2. Okay. Now, could y'all find the least common multiple of this? And instead of 32, I meant to write here 64. So let's do that. And then if y'all notice, we can use the prime factorization you already found. So then think about how from that you would get the least common multiple. Now we know the phrasing of least common multiple no longer cares about common primes like greatest common factor does, but it says choose every prime that's possible. And if you've got a choice between 2 primes that appear in both, choose the greatest exponent. So particularly here, when we have a 2 to the 6 and a 2 squared, we're definitely going to use the number 2. And then we think about which exponent should we use since it's least common multiple, use the greatest, which would be raised to the 6th power. Now 31 is not common, but we just write down all primes, so we also include times 31. And that would be our least common multiple. Questions there? Okay. Now beginning 5.2 material, if y'all would attempt these true falses on the screen after a minute or so, we'll discuss them. So for our first statement, every integer is positive. We know that's false because the integers not only include things like 1, 2, 3, 4, but they also include 0, -1, -2, -3, etc. Okay. Now every whole number is a natural number. Remember the whole numbers include whereas natural numbers start at 1. So this would be false because we could happen to have the whole number 0. That's not a part of the natural numbers. Next up, did y'all get false? 2 is not less than 1.5. Good. Now this one we might need to simplify first. Negative of a negative actually becomes a positive. So this statement is negative 5 is less than 4, which is false. Again, here we should simplify first. Deal with within the parentheses first. 0 minus 4 is negative 4. So minus a negative becomes a positive. So this is really saying positive 4 is greater than 2, which is a true statement. So remember, as you're simplifying, parentheses, exponents, multiply, divide, add, subtract. And think about it to work with these absolute values. Think about these 3. We know absolute value takes what was either positive or negative and makes it positive. So it's going to take 5, already positive, no changes needed. It'll take negative 5 and change it to positive 5. Now here there's 2 parts to the problem. We need to simplify what's inside absolute values and then apply the negative to it since it's outside. So negative 5 absolute value is positive 5. But then we apply absolute or the negative minus the negative becomes, or sorry, that was the issue. So within the absolute value, we get a positive 5 minus a positive number becomes a negative number. So if y'all would take a moment to simplify these 4 exponents, my hint to you is to watch where the parentheses are to see, are you raising a negative number to the 4th power, or are you raising a number to the 4th power and then applying a negative? Now, if we were typing this into our calculator for the first one, since the negative 3 is inside the parentheses, we'd want to make sure we type parentheses minus 3, close parentheses, exponent 4, and there we would get a positive 81. Now, this is different from the next one because here, since the parentheses are not written, it's implied that it's the 3 raised to the 4th power and then you apply the negative. If we had wanted it the other ways, we would have to leave the negative 3 offset in parentheses like we did above. So this is saying, find out what is 3 raised to the 4th and then apply the negative. 3 raised to the 4th is 81. When we apply the negative, we get negative 81. So here, we've got 2 steps. Figure out what's inside the parentheses first and then apply the negative. Negative 3 raised to the 4th power is positive 81. And then we apply the negative. Whereas as we simplify this, we've got negative 3 raised to the 4th minus a negative becomes a positive. Now on the next 2 operations, remember your parentheses, exponents, multiply, divide, add, and subtract. Do you agree with these values? Any questions? Okay, now next up to 5.3. You're working a lot with fractions, so we are asked to reduce 42 to lowest terms. You can just gradually reduce till you get it simplified, but if you want a way that will always work, you could write the prime factorization of both and then cancel any common terms. So approach whatever method you prefer. I'll do the prime factorization method. So 1, 2 from above cancels with 1, 2 below. 1, 7 above cancels with 1, 7 below. And we should get 3 halves as our final value. Next up, we're changing mixed numbers to improper fractions. Now the procedure for mixed numbers to improper fractions. Remember, you always multiply the whole number by the bottom of the fraction because we have 7 of these 8s. Now how many would that be? 7 times 8 is 56, so we have 56 over 8 is what it's pretty much saying, plus 1 over 8, and we get 57 over 8. So the way we think about this is we take 7 times 8 is 56, add the 1 to it, gets us to 57, and you're always over whatever you originally had as your denominator. Now the reverse is we'll change this mixed number to an improper fraction. So the first thing is you do the division on your calculator, 26 divided by 5. It goes in 5 times perfectly plus the remainder. So what we write down is it goes in 5 times perfectly. And we know the bottom stays over 5, so that stays the time same. Now we wanted to get to 26 over 5, but currently we have 5 times 5. We have 25 of them accounted for, so do y'all agree we just need one more as the leftover? So this would be 5 1/5. Next, we had the difference between multiplying and dividing fractions. Remember, in multiply, top times top, bottom times bottom. And then it does say reduce your answer to lowest terms if necessary. And then for dividing fractions, it was keep the first fraction, change the sign to multiplication, flip the second. We'll give everybody a minute to attempt this on their own. And 4/15 is already in lowest terms. So for multiplying top times top, bottom times bottom, For dividing, keep the first fraction, change the sign to multiplication, flip the second. Okay. Now let's subtract and then reduce to lowest terms. And then when you're finished with that, add and reduce to lowest terms. Remember, the key detail here is you need to first get a common denominator by multiplying each term, if necessary, by a carefully chosen one, which is anything over itself. So we know the least common denominator of 3 and 8 is 24. So if I multiply the 2/3 by 8 over 8, that's going to create a 24 in my denominator, but I'm still not changing the problem because 8 over 8 is 1. Similarly, if I multiply 3/8 by 3 over 3, I'm going to get the least common denominator of 24, but I'm still not changing the problem because that's 1. So we get 16 over 24 minus 9 over 24. And I believe that should leave us with 7 over 24, which, since 7 is a prime number, it's already in lowest terms. Good. So similarly, add and reduce to lowest terms is a similar process. Here we think about the most common, least common multiple between 3 and 5, and that would be 15. So we multiply by something chosen to give us the same denominator. So I want to get a 15 at the bottom, so 3 times 5, but of course this has to be multiplied by 5 as well. And y'all agree with 22 over 15? Now 22 is divisible by 2 and 11. 15 is divisible by 3 and 5. There's nothing in common there, so it is in lowest terms. Doesn't have to be simplified further. Now we're in section 5.5. Everybody take a moment to think about these true and false statements. Okay, so every natural number is positive. We know that's true because the natural numbers start at 1 and continue outward, so that's a true statement. Every natural number is negative is false, they're all positive. Every integer is a rational number. Now that's going to be true because if I start with an integer, for instance, like 3, I can write it as a rational number by putting it over 1. Anything over 1 is itself, or equivalently like 6 over 2. However, it's going to be false that every rational number is, and doesn't mean every rational number can be turned into an integer. For instance, 1/2 is a rational number. That is definitely not an integer. Okay, think about, there's a few possible answers for our next two questions. So what is an integer between 2.5 and 5? So here we could accept the number 3, we could accept the number 4, and those would be between 2.5 and 5. Now, what is a whole number that is greater than 14 but less than or equal to 18? Think of all the possible allowed answers there. So could we include 14? Not here because it's strictly greater than. Had it said greater than or equal to, yes, but we can't here. So whole numbers are the positive integers and 0, so greater than 14. We've got to start at 15. But based on the phrasing, do we agree that I could include 18 because it did say less than or equal to? And just if we had typed in any of those numbers, it would be correct. Now, next up, we had some rules about different properties that always occur in the number systems we're working with, but we just kind of gave names to them so we could discuss them. So think about which property is shown in each of the two statements. The first thing is saying that if you add something and then multiply, it's equivalent to multiplying the two things first and then adding. That would be the distributive statement. It's saying that you can distribute the multiplication across addition. Whereas our next one is saying something times something equals 1. And if we remember back from this section, 1 is the multiplicative identity. So that would be showing the inverse property. The idea that if you start someplace, you can multiply by something to get back to the identity. And in the notes, we had a few different examples of these different properties. For instance, if something was showing the identity property, we would want to show that something plus something doesn't change it at all, or something times something doesn't change it. So for instance, in this case, 5 times 1 equals 5. That would be the identity. Now 5.6, we're dealing with some exponents. So particularly in this notation, like we saw in our quizzes, we were writing this expression, it would be 3 raised to what exponent, and that's what we type in the box. So if y'all think about these answers. We know that when the same base is being multiplied, the exponents add, so 4 plus 2 is to the 6th power. However, when you've got one thing to an exponent raised to another exponent, in that case, the exponents multiply. So 4 times 2 would be 8. When you've got the same base to an exponent divided by same base to an exponent, you subtract their exponents in the proper order. Top exponent minus bottom, so 4 minus 2 is positive 2. And then finally, if we wanted to rewrite 2 to a negative power, we know that's the same thing as 1 over 2 to the 5th, which is what we're being put to the positive 5 power. So remember, negative exponents can always be rewritten as 1 over that expression to the positive version of the exponent. And take a moment to think about this distinction. 123 raised to the 0 versus 123 times 0. Joey, anything raised to the 0 is 1, but anything multiplied by 0 is 0. Good. So the first one would be 1, whereas the second one would be 0. So next up is scientific notation. Take a moment to rewrite these two expressions out of scientific notation. We know being raised to a positive exponent in scientific notation, when we rewrite it in our normal notation, it should grow to be a larger number. Being raised to a negative number in scientific notation, when we rewrite it, should grow to be a smaller number. So specifically, we're going to find the decimal place and move it 5 places to the right. 1, 2, 3, 4, 5. Everywhere there was not a number, we're going to add in a 0. So this is 2, 5, 6, 3, 0, 0. Now our next one, instead of going to the right, we're going to go to the left. So I'm going to rewrite my number here. 1, 2, 3, 4, 5. We get that number. Now, that was going from scientific notation to ours, so let's see how would we go to scientific notation. In that case, do we agree this is a very large number that needs to be written in scientific notation? So already, should you expect a positive or negative exponent? Positive. So we know it's something times 10 to, and we expect a positive number. And then the way you go about it is you find the decimal place where it currently is. If there's not one listed, it's to the right of the last listed digit. And you see how many places do I have to move this in order for it to be a single number, decimal place, whatever else comes. So we want a number between 1 and 10 represented. So go over 1, 2, 3, 4, 5. At this point, I shouldn't stop at 5 movements because y'all see it's 23. It needs to be between 1 and 10, so we go over 6. And that's 2.36 times 10 to the 6 because I moved over 6 times. 3, 4, 5, 6. Now the next one is a very small number, so we already are anticipating when we write it in scientific notation, it should be to a negative number. Similarly, we find the decimal place and move. It's here. 1, 2, 3, 4, 5. Now at this point I stop because if right now it's 2.351, if I go over one more, it would be 23.51, and we know it should be between less than 10. So let's see, that was moving over 1, 2, 3, 4, 5 movements. So it's to the negative 5, 2.351. Times 10 to the negative 5. Okay. Now when we multiply things in scientific numerals, think about grouping the like terms. So we're going to take the multiply this times this, multiply this times this. So you have 2.12 times times 10 to the 4th multiplied by Now here we're multiplying same base, so we know we add the exponents. 4 plus negative 2 is positive 2. So we should end up with this. Similarly with dividing, you divide the like terms, this divided by this divided by this. So 4.8 divided by 1.2 is exactly 4. And then when we think about this, we know same base to an exponent divided by same base to an exponent. You subtract the exponents, top minus bottom, so 3 minus 6 is negative 3. And we should get 4 times 10 to the negative 3. On our last section, we are dealing with sequences, arithmetic, and geometric. So let's find the first four terms of the arithmetic sequence, whose first term, a sub 1, is 8, and the common difference, what you add each term, is negative 3. So if y'all can write out the first four. The first one was given to us, that's kind of given away 8. And then each term you add negative 3, so 8 plus negative 3 is positive 5. Positive 5 plus negative 3 is positive 2. Positive 2 plus negative 3 is negative 1.